The topic we are going to today is the refrigeration cycle. Earlier we have seen that one of the statements of the second law belonged to Clausius, where we have proven that it is not possible to construct a device whose sole function is to transfer heat from a cold source to a hot sink and operate in cycle. But when we add a component that does work on the system, that device becomes possible. We have demonstrated that it is possible to construct that device. We have even evaluated what is called the coefficient of performance was comparing the amount of work we have done to remove the heat from the cold sink. So our objective is this, to remove heat from a cold source. And the way we accomplish is by doing work. So how much work I need to do to remove how much heat is the verbal description. And this is the identifier of the refrigeration cycles. The larger the coefficient of performance, the better our refrigeration cycle is. So from that basis, we are going to now learn how our refrigerators and air conditioners work, and we will have in the meantime, certain aspects of those designs, especially the refrigeration fluid. So let's start by constructing a refrigeration cycle. This refrigeration cycle is going to be based on the capacity to absorb heat at lower temperatures and the capacity to release heat at higher temperatures. Now, in order to be able to understand this, let's go back and remember our vapor-liquid equilibrium dome from a PV diagram. Perhaps it's better that I plot this here, that we have a PV diagram. This is our vapor-liquid dome. This is our isotherm. This is going to be our T-hot. And this is going to be our T-cold isotherm, right? As we go down in this diagram, the temperatures are going to decrease. As you see, the lower temperatures require lower pressures to boil or condense. Higher temperatures require higher pressures to boil and condense. If I'm moving in this direction, I'm condensing. If I'm moving in the opposing direction, I'm boiling. Now, when we look at this diagram, it must be clear to you that when I'm condensing a fluid, I need to discard energy in order to bring the molecules closer together, in order to take the extra translational degree of freedom from the gas phase or vapor phase molecules to bring them together and to condense. So condensation is a means of discarding heat or energy. Boiling is absorption of heat. So if I'm going to boil a substance, I have to supply energy, I have to provide energy. Now, if I'm going to, so let me just make sure that my arrows are showing in the correct directions with the correct color. Yeah. If I'm boiling at a lower temperature, it means that my fluid can absorb energy at that lower temperature. And if I'm condensing at a higher temperature, it means that my fluid can discard energy at this higher temperature. So this is the principle that we are going to be using in designing our refrigeration cycle. We are going to boil a fluid at a lower temperature in order to absorb heat at this lower temperature, and we are going to take that fluid, increase its pressure. How? By doing work. And we are going to condense this fluid at a higher pressure. Now that we have the PV diagram, let's translate this information onto a pH diagram also, which we will use to solve our refrigeration cycle problems. So I'm going to generate a pressure enthalpy diagram. Why we have this pH? It's just because of its convenience. I'm going to draw the pH diagram of an unknown fluid, but we will discuss this fluid and its merits, and we will then learn how we're going to use them to do the refrigeration as the lecture progresses. So here we have pressure of the fluid. Here we have the enthalpy of the fluid. We have vapor-liquid coexistence curve here, and we're going to have isotherms that are going through this, similar to the isotherms that we have here. Let's leave this one here and let's come back and start designing our refrigeration cycle. Our refrigeration cycle is going to be a boiler which is going to operate at T cold, or it is not a real vigorous boiling, it is a smooth evaporation, so we call this evaporator. Which is going to absorb heat at T cold. I have a vapor which is at a lower pressure, which I need to compress. By doing work on it. Let's put there dots. I'm going to take this compressed vapor into a condenser. And of course, I have condensed my fluid at this high pressure. Let's call this P low. Let's call this pH. All right. And I now have to expand this fluid to the pressure that I need. There are several ways of doing this. Let me expand in this case using a turbine and obtain a shaft work and be super energetically efficient. So I will call this W sub C for the compressor work. I'm going to do WT for the turbine work, and I have now sketched a Rankine refrigeration cycle. So the steam engine was the Rankine power cycle. We were operating in one direction, and when we operate this cycle in the opposing direction, we generate a refrigeration cycle. The direction of the cycle is like this. We are boiling at low temperature, condensing at high temperature, in opposition to a power cycle. Now let me put these on the pH diagram, pressure enthalpy diagram. Now my evaporator, let's label those as states 1, 2, 3, and 4. My evaporator is at this low pressure, low temperature. This is my state 1, and it is going to, somewhere around is this state 1, let me say. This is not exactly state 1, so let me be a little bit more rigorous in what I'm saying. All right. Somewhere along this line, I have my state 1. I don't know yet where. All right, but this is my constant low pressure line, P sub L. So it's a horizontal line. This is P sub L. All right. I evaporated my liquid up until I have a saturated vapor. That is the saturated vapor point. That's my point 2. Now, between point 2 and 3, I'm going to have an ideal compressor. My ideal compressor is going to operate reversibly and adiabatically. So let me start by writing my balance equations between points 2 and 3 here, and then I will come back for the points 1 and 2. Now between points 2 and 3, I have a reversible and adiabatic compressor. So the points between 2 and 3 looks like that I have an open system, and it looks like that this system is operating at steady state. So let's keep that in mind, that the operation is a steady state. In other words, we don't have any time dependencies, neither in the mass balance, nor in the energy balance, nor in the entropy balance. So the steady state condition in the mass balance says that there is a constant m dot. A constant mass flow rate is circulating in the cycle. The reversible and adiabatic condition apply to the entropy balance along with the steady state condition. That my term here, ds over dt, disappear. Adiabatic condition indicates that I lost this term. Reversibility reflects that I lost this term. And as a result, in my compressor, S2 is equal to S3. On my pH diagram, the constant entropy lines go like this. Let me use a different color. the constant entropy lines go like this. All right? So I'm going to follow a constant entropy line until I arrive at the high pressure P sub H at point 3. So let me label my P sub H. So as a result, my system is going to navigate along this constant entropy line. This is my turbine. No, this is my compressor. I should be much more careful. This is my compressor. And here I'm at point 3. Despite I didn't know the full state of point 3 with the exception of its pressure, by knowing the process, I was able to generate a state variable that took me from point 2 to point 3. So between point 2 and 3, I have a reversible and adiabatic operation where I keep entropies constant, and my energy balance reduces to the following. For the steady state condition, I lose this. For the adiabatic condition, I lose this. This is a rigid device. This term also disappears. And I have 0 equals to m dot, which is constant, h. Now, what comes in is 2. What goes out is 3 plus the shaft work. Shaft work of the compressor. Now, if I know H2, if I know H3, I can calculate the shaft work that I need to supply to the compressor. I know H2, right? I can read it. I know H3. I can read it. I can determine the amount of energy that I'm going to supply to the compressor. Now, let's go to the condenser. Condenser operates at constant pressure, and it follows this line all the way to the saturated liquid. So this is the condenser. This line corresponds to the condenser. All right. And I'm now at state 4. Now, given that I know the pressure and given that I know that this is a saturated liquid, allows me to determine all the state variables with which I can calculate the enthalpy. So between points 3 and 4, I have a reversible isobaric condenser. And this reversible and isobaric condenser is subject to the same energy balance, operates at steady state, and m dot H in is now H3, H out is now H4, and I have Q sub H. All right. So from here, I can now evaluate Q sub H. Now I'm going to find out where my turbine is going to take me. Now this turbine is going to be subject to the same conditions as my compressor. It is going to operate reversibly and adiabatically. In other words, isentropically. In other words, I need to find the constant entropy line that goes through here. All right. So this is my constant entropy line. And my turbine is going to follow this constant entropy line. All right? So this is my point 1. All right? This is my point 1. I know it's enthalpy now. Let me just draw this line in a way that it follows the constant entropy line. Okay? Now it is better. I hope it is clear that we can see both the pink line and the yellow line. All right, this is my point 1. So between point 4 and 1, I have a reversible and adiabatic turbine, which operates at constant entropy. In other words, S4 is equal to S1, and our energy balance is 0 equals to m dot H in. Into the turbine, stream 4 enters, H out. Out of the turbine, stream 1 leaves, plus work turbine. Now I can calculate turbine work. Now that I know my state 1, between 1 and 2, here we have turbine. And this is our evaporator. Our arrows go like this. And now I'm going to use this space between points 1 and 2. I have reversible isobaric evaporator, and this system operates at steady state. M that is constant, inlet is H1, outlet is H2, and this is Q sub C. So with this set of energy balances, now I can calculate the coefficient of performance. All right, let's do that. For the coefficient of performance, now I can read, if I have the pH diagram, if I have this information, I can calculate everything, and those diagrams are available in textbooks of thermodynamics and on the internet. All right, so let's just get the coefficient of performance. What I need to remove is Q sub C. So this is one aspect of my coefficient of performance. The other is work. This should be the net work, right? For this Rankine refrigeration cycle, it is the network. So network is going to be the work that I did in the compressor and the work I obtained from the turbine. It's the summation of the two. So the coefficient of performance of a Rankine refrigeration cycle is Q sub C. What is Q sub C? It is m dot H2 minus H1 divided by the network. Network is compressor work, m dot. Compressor work is H3 minus H2 plus m dot turbine work. Turbine work is m dot H1 minus H4. So let's check if we have everything correct and in place. M dot H2 minus H1 is Q sub C. M dot H3 minus H2 is the compressor work. M dot H1 minus H4 is the turbine work. And those m dots cancel. All right. And this is our coefficient of performance for the Rankine refrigeration cycle. All right. Those cycles are the ones that you would find in your own refrigerator. In your own refrigerator, the evaporator is in the freezer. All right. So this is the freezer domain of your refrigerator. This is the freezer of your refrigerator. And the condenser in older type of refrigerators is the black grid in the back of the refrigerator. All right. So let's write where they belong. So this is the freezer. And in the older time designs of the refrigerators, it's the black grid in the back. All right. So if this is your refrigerator, the front view, all right. If this is your freezer, this is where we need to remove heat in order to keep at this low temperature. We don't want heat to sneak into here. Heat is going to sneak into here. That is the natural direction. But we would like to remove heat from here. This is the evaporator domain. So what is the temperature in your freezer? All right, I will wait a few seconds just to ask yourself this question. And perhaps go and check the internet. All right, few seconds. The temperature in the freezer is around minus 17 degrees Celsius. And the fancy story about this minus 17 degrees Celsius is that microorganisms just stop growing at a fast rate below that temperature. All right, you can maintain anything healthy for over 6 months if you maintain this temperature. Right? That's the fancy number. Now this is the front view of your freezer. The back view of your freezer, this is the front, right? In the back, in the older designs, you find a dark black grid, right? This dark black grid is the condenser. And the reason we have this black huge grid is to provide the surface area for efficient heat transfer. We are going to condense our fluid and we are going to discard our heat to the room, and the temperature gradient is very small. To compensate for it, we need a little bit high surface area, and this is our condenser. All right? And the condenser is going to discharge to room. But the room temperature is going to change from season to season. So we need to design the system in such a way that it should be able to discard heat to possible very high temperatures. Now, for example, in very hot summers, we might have a freezer or refrigerator outside, and typical ambient temperatures are 40 degrees Celsius. In order to be able to discard heat to the environment, I need to have a condenser temperature that is higher than typical ambient temperature. So if the ambient temperature is 40 degrees Celsius, I should have a temperature of around 45 and 50 degrees Celsius in order to be able to discard heat to the environment. So now we have our temperatures. Let us write it here. So this T sub C is around minus 17 degrees Celsius. This T sub H is around 50 degrees Celsius. All right? So this is minus 17 degrees Celsius, and this is 50 degrees Celsius. Now it's, excuse me. Now let's just step back and ask ourselves this question now. Which fluid is going to boil at minus 17 degrees Celsius around atmospheric pressures, right? I don't really want to play with vacuum. Either one of those pressures should be atmospheric, and I would rather have this at atmospheric pressures, all right? So I need a fluid that is going to boil at minus 17 degrees Celsius at atmospheric pressures, and that fluid should condense at reasonable pressures, all right? Not too high pressures, when its boiling point is around 50 degrees Celsius. Now, what could be such a fluid? Now, when these refrigeration cycles have been invented, of course, we had to resort to the natural fluids, and the fluid of choice, refrigeration fluid of choice, was ammonia. Ammonia actually indeed is a good refrigeration fluid. Why? Because its boiling point at atmospheric pressure is minus 33 degrees Celsius. This is very good in terms of our requirements. It's below minus 17. It's not too low than minus 17. And it also fulfills conditions of this high pressure behavior. But ammonia is a corrosive liquid, and the metallic components of the refrigerators couldn't withstand. So there were alternative material that was being sought, and that alternative material had to fulfill the following requirements. It should have boiling point at that temperature, at atmospheric pressure, boiling point at this temperature at around, say, 5 atmospheres, 10 atmospheres, not more than that, right? So in that ballpark. And it should be stable. It shouldn't be toxic. It shouldn't be flammable. It shouldn't be combustible, and so on and so forth. So let's list our requirements. Shouldn't be toxic. Shouldn't be flammable. Shouldn't be combustible. And this is the boiling point range given those pressures, and of course the science of chemistry has been taking up. So it was then possible to order chemists to find such molecules. And those molecules have been looked for and found, all right? Those molecules which were stable, boiling at this temperature under that pressure, boiling at this temperature under this pressure, not flammable, not toxic, not combustible, were called freons. All right? The family name of the molecules are called freons. Well, those freons have been used until late 80s, when it was discovered that those freons, which are used in our refrigerators and in sprays, and they were very freely used almost anywhere industry demanded refrigeration or spraying, actually they were so stable that they remained intact until above the stratosphere, and they were able to destroy the ozone layer. The molecules were acting as catalysts, where ozone molecules were cracking into oxygen atom and oxygen molecule, and then forming new oxygen molecules. So there were huge holes in the ozone layer that were discovered, and the ozone layer, of course, is protecting the penetration of excessive amount of UV radiation from sun. After this discovery, of course, chemists had to do their homework and improve the performance of their molecules. That freons, which are a family known as chlorofluorocarbons, are replaced now with the hydrofluorocarbons. So we have hydrogen, fluoride, and carbon in those molecules. This new family of the refrigerants that we use in our refrigerators are called hydrofluorocarbons, and the particular ones we use HF134A, HFC134A, and the pH diagram of this hydrofluorocarbon is available in our textbooks, whichever is you're using, and also the internet provides the pH diagrams. Now we are going to use HFC134A in our analysis of our refrigeration cycle, but this part of the lecture was to give you a perspective of how those molecules are being invented. The molecular structure determines a lot of physical properties, thermodynamic properties, and now we have the capacity of demanding a molecule that can have this boiling temperature at this pressure, this boiling temperature at that pressure, and it is possible to synthesize those molecules. But of course, still HFC134A is not an innocent molecule. Our objective should be to be very careful when we are using it, and very careful with our use of freezers, refrigerators, and also our air conditioners. We shouldn't be very happy about it. We should understand the impacts of those devices that we are using on our environment for the present and also for the future. Now, this Rankine refrigeration cycle, along with the theory behind it, was for an efficient refrigeration cycle. The little bit less efficient cycle is called the vapor compression refrigeration cycle. I will just create a small frame here and discuss the vapor compression refrigeration cycle in this small frame. Okay. Vapor compression. Refrigeration cycle. Okay. Vapor compression refrigeration cycle does vapor compression. Yes, this step is the same. We have vapor compression. But then the turbine is missing in the vapor compression refrigeration cycle. What we do is, of course, we have this evaporator condenser diagram. In our flow chart, we need a compressor to compress our vapor. We absorb heat. We are going to discard heat. Now, coming back from this high pressure domain to a low pressure domain is achieved by a process called throttling. So we have a throttle valve. In that throttle valve, we are not concerned about obtaining work. We are a little bit less concerned about our need of having an efficient refrigeration process. We are more concerned about being able to release the pressure and bring the fluid to the lower pressure. So in this vapor compression refrigeration cycle, let's again label our states 1, 2, 3, and 4, similar to the Rankine refrigeration cycle. You see, everything is the same. Between point 1 and 2, I have an evaporator. Between point 1 and 2, I have an evaporator. Between 2 and 3, I have a compressor. Between 2 and 3, I have a compressor. Between 3 and 4, I have a condenser. Between 3 and 4, I have a condenser. So between 4 and 1, I have a different process unit. All I have to do is to write the energy balance for that process unit and just let me see where my coefficient of performance is going to settle itself. So between points 4 and 1, I have a throttle valve, and in that throttle valve, the process is at steady state. This term disappears. The process, the valve is rigid. I don't have this term. There is no shaft work. And the process is so rapid that there is not sufficient time for heat transfer. So my energy balance turns out to be 0 equals to m dot h4 minus h1. Now notice that this process turned out to be a constant enthalpy process. All right? So the throttling process, let me see if a white pen is going to work here. It should take me down. Unfortunately, this is not going to help me. That I'm going to have a constant, here, constant enthalpy straight vertical line. So this is the throttle valve. All right, so this is my 1 prime. So let me make this 1 prime. Let me make this 1 prime. All right? Now, given that the area under the rectangle is smaller, means that my efficiency is going to be slightly lower, because I'm not able to make good use of this work here to keep the denominator smaller. So the coefficient of performance of the vapor compression refrigeration cycle is going to be the top H2 m dot H2 minus H1 prime, right? I'm not all the way here, I'm at 1 prime. So this, I'm just removing less heat. All right, at the expense of more work. M dot H3 minus H3 minus H2. Okay? I'm not benefiting the work that I obtained from the turbine. My denominator is larger. My numerator is smaller, so the coefficient of performance of a vapor compression refrigeration cycle is smaller than the coefficient of performance of a Rankine refrigeration cycle. So this is how we have, type A, type AA, type AAA energy efficiencies in our refrigerators. Now there is one more thing that we engineers have learned along the path that we were designing those refrigerators. Now the newer refrigerators, new generation of refrigerators, they don't have a condenser in the back. The condenser in the new generation of refrigerators are in the vegetable compartment, all right? And the newer generation of refrigerators have the freezers in the bottom and the vegetable compartments on the top of the refrigerator. So in doing so this is the old generation, huh? The newer generation of the refrigerators look like this. They have 2 doors. All right? Mostly, right? Of course, there is the art part of their design. I'm going to talk about the engineering part without referring to the art part of the design. So this is the upper compartment. We have a door, all right? So let's call this handle, all right? And this is the lower part of the refrigerator, all right? It has a door. This is the other handle of the lower compartment. Now in the lower compartment we have the freezer. The benefit of putting the freezer in the bottom than to the top is to be able to use the natural direction, all right? So if nature demands something, don't run against it, all right? Use it. So what is the law of the nature? When air gets warmer, it moves up. So I don't have to deal with keeping this part cool. All I have to do is to let the rising air from the freezer to the vegetable compartment. The second thing is that why do I have to discard heat to the outside environment, why can't I use this vegetable compartment as my heat sink? So if I put my evaporator here, if I have to put my evaporator in the freezer, and if I put my condenser in the upper compartment, what are the temperatures that I need in the upper compartment? Maximum 5 degrees Celsius. It should be greater than 5 degrees Celsius. What is the reason of 5 degrees Celsius? Because volume of water maximizes when the temperature is 4 degrees Celsius. We really don't want the water moisture in our fruits and vegetables just to expand and physically destroy, denature our fruits and vegetables that we keep in our refrigerator. So keeping temperatures slightly greater than 5 degrees Celsius is needed in that part. Now put your condenser inside your refrigerator. Take the temperatures from 50 degrees Celsius to about 5 degrees Celsius. All right, so this is the new generation, 5 degrees Celsius. So when I do that, my efficiencies just go very, very high. So this is the new generation of the refrigeration process. But of course, the fact that we have refrigerators shouldn't make us use it irresponsibly. By irresponsible use of refrigeration, I mean that instead of cooking and eating fresh food, we shouldn't rely on frozens too much. And also we shouldn't buy stock and trash our food. Right? The current problem is that we are wasting about 40% of our food simply by just storing in refrigerators, forgetting them there, forgetting to eat them, and we are trashing while half of the world is starving. So we have to be responsible with the way we use our refrigerators. This lecture had touched upon a couple of aspects of engineering and engineering ethics. Just the take-home message is not only thermodynamics, but also how we use this thermodynamics in generating comfort around ourselves. Remember, design efficient systems. Remember, go with the flow of nature, not too much against it. Remember, when you have something too good to be true, challenge that. We had an ozone layer problem that bothered us for quite a while, and now we have this climate change problem that is bothering us, and we are learning from it. Not just do your thermodynamics right, but just think deeper about it.